What happens when segments are divided proportionally? Now, when segments are divided proportionally, it doesn't necessarily mean, why did they do that? Try again. It doesn't necessarily mean that the segments are the same length. But what it does mean, if we can label these points, is that we have a proportion that's formed with the lengths. So, AB will be to DE as BC is to EF. Now that's just one proportion that can be formed there. We could also, using property of proportion, as long as we keep our direction the same, we're forming a correct proportion. For example, we could say AB is to BC as DE is to EF. Or we could even say that AB is to the whole length, AC. Because remember the property of proportions where you can add the denominator to the numerator. AB plus BC over BC is the same thing as AB over AC equals DE over DF equals DE plus EF over EF. So all the properties of proportions here are going to be true. They are divided proportionally. Now, theorem 7.3 says that if a line parallel to one side of a triangle intersects the other two sides, then it divides those sides proportionally. This is the triangle proportionality theorem. Okay, Dustin and Branson.
Not ready.
Okay, but don't be talking. You missed.
Oh, she right back.
Okay. I actually need to try to keep my attention here, and I'm having hard to do that. If a line that is parallel to one side of a triangle intersects the other two sides, then it divides those sides proportionally. So what I need here is a triangle with a line parallel to one of the sides. and intersecting the other two sides. So here we're going to be given that DE is parallel to AC. What we want to prove is that that line divides those sides proportionally. So we want to prove that BD, I'm trying to think what is the easiest way to prove it. Okay. That AD is to DB as CE is to EB. What I know is that I have some similar triangles that are formed by this parallel line. I know that corresponding angles are congruent. So triangle DBE will be similar to triangle ABC. And this means that we have some sides that are proportional. AB will be to DB as CB is to EB. That's by definition similar triangles. When triangles are similar, their corresponding sides are proportional and their corresponding angles are congruent. Now what I can do is think of AB as AD plus DB. So what I have is AB is to AD plus BE. Let me try again. AB is the one. So AD plus DB is to DB as, and I can think of CB as CE plus EB. That's just segment addition postulate. Now I can use property proportion. See how this is the denominator, dB, and this is the denominator, EB? By property of proportions, then going the other direction, I will have AD is to DB as CE is to EB. We have a corollary in another theorem, but the other theorem might as well be another corollary. So it doesn't take us that long. They're both direct results of the triangle proportionality theorem. So first off, the corollary. Corollary says if three parallel lines intersect two transversals, then they divide the transversals proportionally. So we have three parallel lines. These lines are not necessarily evenly spaced. They are just three parallel lines that intersect two transversals. These transversals can be at any angle. So I could take these transversals and change their angle to any angle. And this theorem or corollary will still be true. If three parallel lines intersect two transversals, they divide the transversals proportionally.
Oh, that's that big gap right there.
So what proportionally means is that AB will be to BC as DE is to EF. The ratios will be the same. So our given here is that AD, BE, and CF are parallel. What we're proving is that AB will be to BC as DE is to EF. And the reason why it's true is because I can draw a segment, say from C to D. That gives us two triangles. We'll call this new point P, where that segment intersects line BE. And from the triangle proportionality theorem, which was theorem 7.3, I know that these following proportions must be true. In triangle ACD, this line is parallel to AD and intersects side AC and CD. So it must divide those two segments proportionally. When a line is parallel to one side of a triangle and cuts the other two or intersects the other two, it has to divide it proportionally. So, from that theorem, I know that AB will be to BC as DP is to PC. Now look at triangle DCF. In triangle DCF, what we have is the same thing happening. This line that's parallel to CF and goes through triangle DCF intersects the other two sides, so has to cut those two sides proportionally. Which means that DP is to PC as DE is to EF. Now put these two pieces together with the transitive property or the substitution property. Since both AB to BC and DE to EF are equal to the same ratio, they have to be equal to each other. So AB to BC has to equal DE to EF by the transitive property. All right, now we have one more theorem, which is the triangle angle bisector theorem, or theorem 7.4. What this theorem says is if a ray bisects the angle of a triangle, then it will divide the opposite side into segments that are proportional to the other two sides of the triangle. So when a ray bisects an angle of a triangle, then it will divide the opposite side into pieces that are proportional to the other two sides of the triangle. So what we have here is a triangle. It's a triangle. Thank you, thank you. And we have a ray that bisects one of the angles. Of the triangle. Bisects the angle. So our given here is that AD bisects angle BAC. What we want to prove is that this opposite side, BC, is divided into pieces that are proportional to the other two sides of the triangle, BA and AC. So we want to prove that BD is to DC as BA is to AC. Now to get there, what I'm going to do is I'm going to extend side BA. Let me do it in blue so it kind of changes the color here. I'm going to extend side BA. And then we're going to draw a line through C that is parallel to AD. My line got a little crooked. Now when we do this, because we have parallel lines, we have some congruent angles. I'm going to try to do this again. Still got a crook in my line. Let me cheat. Yes, it is. That's the garbage pile. Okay, parallel. That looks like it might do it. Okay. Now, because we have parallel lines, we have some congruent angles. We have alternate interior angles are congruent, so these angles are congruent. And we have corresponding angles are congruent. So these angles are congruent, but don't we know that that is an angle bisector? So by substitution, I should be able to show that, in fact, these angles are the same as those angles. Okay? That's what we're going to use to help us prove this proportion. So I'm going to shrink this so I have a little room. Tommy and Var. So now, if you can give me your attention, our last proof here. Okay. First off, to do a proof where you draw auxiliary lines, you have to explain the auxiliary lines. So we extended side BA. And we drew a line through C that intersected that line and is parallel to AD.
We're not there yet.
Since alternate interior angles are congruent, corresponding angles are congruent, and a bisected angle forms two congruent angles. So I'm going to say since lines are parallel, corresponding angles are congruent, and alternate interior angles are congruent. We'll number these angles so we can refer to them. Angle 1 and 2 are alternate interior angles. Angles 3 and 4 are corresponding angles. Because angle 3 is congruent to angle 1, by substitution, angle 4 must be congruent to angle 2.
Move.
Now that I have angle 2 and angle 4 congruent, I know that I have an isosceles triangle. Which means, call this point P so we have a point to refer to. AP and AC are equal. This is theorem 4.2, the base angle of an isosceles triangle theorem. So my theorem 4.2, AP is equal to AC. By theorem 7.3, however, there's the next two. By theorem 7.3, which is our triangle proportionality theorem, you see how you have a triangle with AD parallel to one of the sides, PC. Look at triangle BPC. You have a line that is parallel to one of the sides and intersects the other two. So it has to cut it proportionally. So by theorem 7.3, BA will be to AP as BD is to DC. I can't make a D there, let me try again. Now, if I make a substitution, because I know AP and AC are equal, I know that BA will be to AC by substitution as BD is to DC. We have a triangle with a line drawn parallel to one side that intersects the other two sides. We have three parallel lines that intersect two transversals. And we have a triangle with an angle bisector. In each of these three cases, if these are sides length A and B, C and D, then A will be to B as C is to D. If this is side lengths A, B, C, and D, still A will be to B as C is to D. If this is side lengths A, B, C, and D, still A will be to B as C is to D. Using properties of proportions, we can come up with some other proportions that must be true. All we have to do is change our direction. So instead of going down both times, we could go left to right both times. And we come up with A is to C as B is to D. It's the same proportion. Cross multiply AD, BC. It's the same thing you would get with the cross multiplying here, AD, BC. It is the same for both proportions, AD, BC. Instead of going left to right in both cases, we could go bottom to top in both cases. What we cannot do is change our order or go diagonally. You could not go A to D. That's diagonal. That would not work. Okay? We can go right to left in both cases. And the same thing is true here. You could go left to right in both cases. Or you could go, which is what I did here, or you could go bottom to top in both cases. When you keep your order the same, you get a proportion that is true. When these segments are divided proportionally, you can set up many proportions that are true.